Okay. So first, I would like to thank the organizing committee for inviting me and giving the opportunity to give this talk here. And I would like to again talk about the particle motion and acceleration around black hole in the Horava-Lifshitz gravity. So previous talks and today the first plenary talk was about dedicated for this gravity theory and particle motion. So I may somehow to continue on this subject. So this is the outline of the talk. First I will talk about this particle motion around the black hole in Horava model, and then I will talk about some energetic processes around this compact objects in Ks space-time and other Horava-Lifshitz gravity model solutions. So motivation is clear. So the energetic process observed in the active galactic nucleus center and high energy particle emission from the center of the galaxies force us to study the energetic processes around the compact objects, and on the other hand we have some modified theories, and one should interested in to find what is the modification to these new theories on the energy extraction or energetic processes in compact objects within these modified gravities. And we have paid attention to study first the energetic process in this proposed gravity theory, and first we started with the charged particle motion around this Kihagis-Fetzer solution, but we considered the external extra magnetic field, external uniform magnetic field, and in the presence of this magnetic field, the charged particle motion in this space-time, this already introduced this space-time, and we started how the effective potential and the circular motion will affected by this external magnetic field, and you can see how the effective potential changes due to the omega parameter and the epsilon parameter, where epsilon is responsible for the magnetic field and charged particle interaction term in the equation of motion. And you can see that the change due to the magnetic field is farther than central object, while the omega parameter, as it was studied by other authors also, are very significant in the near of the central object. So here you can see that the energy and angular momentum of the particle moving on the circular orbits, and you can see how this energy and angular momentum shifts to the center with decreasing this omega parameter, and while this omega is greater than 1, this dimensionless parameter omega larger than 1 corresponds to the Schwarzschild black hole case, and you can compare how this minimal circular orbits shift to the central object here also. And here again once more this figure, so you can see here how the circular orbits depends on omega parameter, and here we considered the omega, the regular case when the Ks solution has a horizon. For the naked Ks case, you can see the paper by the authors, by Robert and others mentioned before. And here we found an analytic expression for electromagnetic field, and here you can see how the innermost stable circular orbit depends on omega parameter. The main thing is that one can make an estimation for omega parameter using the observation data on accretion disk around the central objects, and making some roughly estimation. One can get the estimation for the omega parameter at the following. So let me now start to talk about the energetic process around the compact object. So first, this is the schematic view of the Penrose process. So Penrose process itself represents some energy extraction mechanism. So if you have some energy and some particle falling down to the, say, rotating black hole, then when it comes into inside the static limit of the let us say Kerr space-time, then inside the so-called ergosphere you can if you have a dividing into two parts, then one part with negative energy falling down to the central objects, and due to the energy conservation, the other particle with higher energy can escape from the capturing of the black hole, which corresponds to the energy extraction. So for this case, we studied another rotating black hole solution in Horava-Lifshitz gravity, and this solution is very similar to the cosmological solution of and you have extra parameter L squared, or we introduced another dimensional parameter delta, and we are interested to study how this parameter will affect to the energetic process around the black hole. So first we started to study the ergosphere due to this delta parameter. So delta is a parameter, is a small parameter depend on L squared, 1 over L squared, and for the different values you can see how the ergosphere shifts, ergosphere of the rotating black hole can be changed, and you can see the increasing the ergosphere in the polar region, which in our point of view is very interesting, since all the energetic processes in the central galaxies are going to be in the polar region, and maybe this can be related somehow to the energetic jet emission mechanisms in the central galaxies. Moreover, we found the extracted energy, the expression for extracted energy by rotating black hole in Horava gravity, and found some linear effect depending on this new parameter delta. And if you have this, if you have a negative value of this expression, then you will obtain some energy extracted, because this this energy corresponds to the increasing of the mass of the central object. If you have a negative value of increasing central object, then you will have a energy extracted energy from the central object. So another mechanism is a particle acceleration mechanism. So if one can consider two-particle collision near the rotating black hole. And then this is the first physics letters paper by Bangladesh Quest, after which the people started intensively study the particle acceleration. So what they found that in the extreme rotating Kerr space-time, for the fine-tuning angular momentum, they observed some infinite energy, center of mass energy of colliding particles. So we also tried to study what happens in the case of this modified space-time, that's modified rotating space-time in this gravity model, and then we observed that if you have this limiting case, when you have a Kerr space-time, you will obtain some the infinite center of mass energy. But if you increase the delta parameter, then you will have some finite energies, and we can say that this is due to this in principle, one of explanation of this center of mass energy can be explained as a splitting of innermost stable circular orbits and even horizon in extreme rotating black hole. But in this case, if you have a non-vanishing delta parameter, then you have a not coinciding ISCO and even horizon for the extreme rotating black hole in this space-time. And another interesting thing we have studied is the silhouette of the black hole, which was also studied by our speaker, by Honza, in his talk for the brain vault models, and we have studied it for the black hole, rotating black hole in this Horava gravity model. So to study this, one should introduce the Celestian coordinates, and observer should observe some black shadow where in the center of bright, let us say bright background, and the shape of this silhouette or shadow is strongly dependent on the parameters of central gravitational object. In this point of view, we studied the equation of motion of photon in this rotating black hole space-time in this modified theory, and defining the impact parameters Xa and eta like this, and this using the standard definition to go to these celestial coordinates, and then one can find the alpha and beta depending on the parameters of central object. And here we have shown some results how the shadow of this central object of this black hole can depend on this delta parameter. You can see here this solid line correspond to the Kerr one, and if you increase the delta parameter, then you can see the decreasing the total radius of this shadow, average radius of the shadow, and you can also observe the distortion of this shape with increasing this delta. The distortion here you can see that more details. So here you can see that with increasing the delta parameter, the average radius of the shadow is going to decrease, and also this distortion parameter is also going to decrease, which means that the shape of the shadow is going to be a circle with increasing the delta parameter. In a typical Kerr space-time, you have opposite effects. With increasing the A parameter, you have more distorted shape. But in this case, the delta has a opposite effect on the shape of the shadow. And also, we studied how the omega parameter will also change for the shape of the black hole. In this case, you can observe that for the KS solution, you have a larger shape of the shadow of the central black hole. And here you can also see how the average radius depends on the omega parameter. So as a conclusion or summary, I would like to summarize the obtained results. So first we obtained the comparing the obtained numerical results and the observation data on this accretion disk. We obtained some estimation on KS solution, and moreover we showed that the energy extraction through Penrose process is more realistic process among the energy extraction in black hole in Horava-Lifshitz scenario. Moreover, in particle acceleration mechanism, the correction of this gravity theory prevents the particles from the acceleration to infinite energy. And moreover, we showed that this delta parameter is also with increasing delta parameter, the distortion parameter and the radius of the shadow of black hole is going to decrease. And we also studied the dependence on KS parameter on shape of this black hole shadow. Okay, thank you.
Thank you, Ahmed.